Hi, it's time for another math. Easy. So we're going to discuss. Well, basically, I'm gonna look at Archimedes. His proof for pi is this famous mathematician, physicist, engineer. He did a bunch of stuff. He was pretty smart. So basically, Archimedes of Syracuse. This is in Greece. Yeah, just a short history lesson on this one here. Basically, he was born in BC around 287 BC. The C means circa. Yeah, and basically it's Latin for around, because no one really knows for sure when he was born, when he died here. Basically, he calculated pi using basic geometry in a recursive manner, or meaning he basically repeated his method over and over again to get a more accurate representation for pi. Basically, he calculated perimeter of regular hexagon using inscribed inside and outside of a circle like this one here, and then he would double he doubled the size until he was satisfied with a 96 side polygon, because basically he knew that pi was just the ratio of the circumference over the diameter by definition. I'll show another proof of why this is true actually, but besides you could just look at it and it's usually is true. So then this one, if you let the diameter is equal to, let's say, 2 times r here, and then he drew a circle. The circle's our radius is r, so r is equals to 1. This is just what he did with his method here. So then pi is equal to circumference divided by 2 times r, which is 1. Yeah, so just circumference divided by 2 here, and then the circumference you approximate it by the perimeter of these of this polygon here, this hexagon in this case here, and then he would double the sides. Yeah, so here's this what I mean by doubling the sides. So all he does is draw another polygon like this, so it's even a closer approximation. Find the area, find the perimeter of that. So he keeps going on, so every single side would be doubled. And now, just before I illustrate how we got this method here, I just want to note that with any inscribed polygon that has the same sides on this one here, and if you inscribe it inside and outside, you could see that there's a symmetry here. If you go from the center here and draw an angle here, it's going to cross both corners. So both corners of these would be exactly the same. So as you can see, all it is it's translated. If you have this side here, translate exactly how it looks, but just bigger with the same angle here. And you can see with this 6-sided one as well. If you draw from the center here, it's exactly the inside and outside inscribed side is exactly follows this line here. So that's all it is. So using this characteristic of circles and inscribing shape inside, we can derive a formula basically that illustrates if this value is x of the current side, we can find the length y here. We'll call this one y. And then from this, we could keep doubling it and doubling it, because you're always going to have the same property regardless of the sides. So if we have just a general side here, this could be for hexagon, polygon, anything like a 90-side polygon, but this is just exaggerate the space here. Basically, if you were to draw like this, yeah, so I just draw a line across it like this, and the radius here from here to here is r, we'll call it equals to 1, just so that the pi is going to be circumference divided by 2. So now, what we can do here, if we call this value x, so this, we'll just extend it here. If this full length across from here to here is x, we'll also call this one z, because this is going to be the outside polygon here. This would be an outer estimate for pi. So we're going to have, we'll call that z here. And now if we were to double the side here, first we'll draw, so this is what Archimedes did. He would, so you draw a line splitting this x into 2, so you're going to have an x over 2 and then x over 2 in this case, and then he would draw it all the way extended out here, and then when you would double the sides, this is going to be y, so this is your new length here. So this is y here. And now what he did, he used Pythagoras to basically, okay, we'll call this side length, to derive a formula for y in terms of x here, and also z in terms of x. You can use similar triangles. So we'll call this b right here. So we have these sides here. Let's just find z in terms of x first. So this length here is going to be z over 2 from basically from here to here. And using similar triangles, well, we know this theta here, we know that, well, if we just go tan theta, tan theta is equal to opposite over adjacent. So there's two triangles here, this one inner and one outer, that both share the same angle. So this is going to be equals to x over 2 divided by a for the inside triangle, that's opposite adjacent. And this also equals to, well, z over 2 over, well, this one here, this is just 1. A plus b is equal to 1 here, because that's going to be, divided by a plus b, and this is equals to 1, because the radius, this equals to r equals to 1. So this equals to z over 2. So if we just Yeah, fix this up, you cancel the 2's, we're gonna get z is equal to x, x over a here. And now using a, you could derive, basically we know this is 1, so we could get a in terms of x using Pythagoras. Yeah, so using Pythagoras, the theorem here, you can see the proof in the video link below, but basically this is going to be 1 is equal to a squared plus x squared, because this is r, and that's hypotenuse, this is adjacent, and this is opposite. So then we could just solve for a is going to equal to, well, plus or minus square root of 1 minus x squared. We just shift it over to this, to that side, and we're not looking at the negative, because in this example, a negative number doesn't mean anything, so we only look at the positive here. So we get a positive, so we'll just plug this back in here. So we have a function for z here. This equals to x over square root 1 minus x. Oh no, this is x over 2, forgot this. X over 2, that's a side. So 1 over x over 2 squared here, forgot to do that, because you can see that the triangle's right there, x over 2. Yeah, so we have a function for z, so this would be our outer perimeter here, and this would actually get an overestimate for pi. So now what we're left to do is basically solve for y in terms of x. So this is what Archimedes did here. So basically you look at these two triangles here. Well, we know that also a plus b is equal to 1. So then we would just find this Pythagoras theorem and then plug in these values for it. So I'll just show it right now. Yeah, so here I just wrote down what we know. This is the right angle triangle there. This is the right angle triangle here. So we gotta get y in terms of x. So then y squared is the hypotenuse, just equals to x over 2 squared plus b squared here. Now we know that b is just equal to, if you rearrange this one, this is r is equal to this. Rearrange it, b is equal to 1 minus a, and this just equals to 1 minus, well, we solved a already, so they're right there. So we can go square root 1 minus x over 2 squared. And we just plug this in here. We're going to get... So yeah, just basically plug this b inside this function here. We're gonna have this one here. So we have a function of y in terms of x now. We can simplify it further by just foiling this out using the FOIL method. You can see my video link below on proof of that. So this is gonna be x over 2 squared plus, now let's FOIL this out. 1 times 1 is just 1, and then we're gonna actually have 2 square root 1 over x over 2 squared. You could just, this is basic foiling. And then plus, this times itself is going to be squared, so we just get rid of the square root. So we're going to have this. Let's get 2 here. So now we could simplify it further. We could add up the 1's in this case, and then we could also cancel this one, x over 2 squared minus x over 2 squared cancels. So we're going to get y squared is equal to 2 minus 2 times square root 1 minus x over 2 squared. So y is just going to be the square root of it. And now this is our function for y here. Now remember, we just solved this for an arbitrary side here. So if we have an initial x, we can double it, and we could use this formula, keep doubling it, and always use this formula here. Yeah, so now with these formulas, all we need to do is find an initial x value, and that depends on our shape. So for this one here, for a 6-sided polygon, so I just split this up in the angles here. So this is 6 angles here, 1, 2, 3, 4, 5, 6. So then, and every single one's going to be the same. And then the total number is 360, so for this one we're going to have 360 degrees divided by 6. This just equals to, well, this is, what is this, 6 times 60 divided by 6 equals to 60 degrees. So this equals to 60 degrees here. So then when we split this, so we'll split this in 2. This is going to be now 30, this one is equal to 60, and this is going to be 30. So we could solve using Pythagoras, or not Pythagoras, just using trigonometry here. And so we're going to have here, this is going to be number x over 2. This is our x value. So all we're doing is trying to find our x value. For this one, this is going to be x, and we're going to split this up like this. And remember, this is, for a square, this is just going to be 45 degrees, because they're all the same here. So this is going to be x over 2. This is going to be 1 here. And then we just use our exact trig ratios. You can see the video link below for that one here. So for tan is 30, I'll just draw this one out. Yeah, so for tan 30, I'll have something like this here, and this would be square root 3 to 1. And yeah, so then this ratio, and then for the 45 degrees, you'll have, yeah, well, 45 is just exactly split in 2, so we're going to have 1 and 1 ratio, and this can be square root 2 here. So then when we're taking here, to solve for x over 2, this is just going to be sine of it. So we're going to go, in this case, sine. This is for the 6-sided polygon. This is a hexagon. Just call it hex. Yeah, so that's hexagon squared. So then basically sine of 30 degrees in this case is just going to be 1 over 2. But then we're using similar triangles. If this is also, the ratio is supposed to be 1 over 2, so we're just going to have x over 2 over 1 equals x over 2 over 1. The 1 doesn't do anything. The 2's cancel. So for this one, we're going to have x equals to 1. And we have 6 sides. So we'll just write that. And then for this one here, sine of 45 degrees is equal to, well, this is going to be 1 over square root 2. And this equals to, well, in this case, well, x over 2 over 1. So just x over 2 over 1. The 1 doesn't do anything. And then we just put the 2 over top. So we're going to get x is equal to square root 2 over 2. So this is for a square, or we'll just go 4 sides. So now what we do for, let's say, the first iteration. Yeah, so for first iteration here, all we do is find this x value here. So then the perimeter of it is just going to be equal to the number of sides for, in this case, where let's say 6 times it by times 1. So that's a perimeter here. And then pi is just going to equal to, yeah, circumference divided by number. Circumference divided by 2. So in this case, it's approximately p divided by 2, and then this one's going to be approximately, yeah, this is going to equal to, well, 6 divided by 2 is equal to 3 here. And then, so then pi has to be greater than this one here, because from this one is the inner triangle, so pi has to be greater than, then we'll just call this one, yeah, well, greater than 3 here. And it's also, it has to be less than if you were doing the outer parameter here. So in this case, we'll go 6 times, well, z. And then yeah, so it has to be less than this one because this is the outer parameter. So so generally speaking, we'll have pi is less than number of sides, yeah, times z over 2. This is the outer perimeter side, and then divided by 2 because it's perimeter divided by 2, and it's going to be greater than, yeah, number of sides times by x, so that side divided by 2. And then when we solve for y is just the new x here. And then the new sides is going to be, number of sides is going to be times by 2. Times by 2 here. So that's what we're going to get. Now I've made an Excel sheet here actually, and so basically here for this one 6 sides here, if this is the hexagon here, so all you have to do is put in whatever this initial input x value is, if it's 1. And then this one is at square root 2 minus 2 square root 1 minus x divided by 2. So this is the new y. So this is the initial is x, and then the new y is just, the y's is going to be the new x. And as you can see, it gets smaller and smaller every time we double. So we double the sides, 6, 12, because we're doubling it. And then the z is just going to be that formula I derived. So we're going to get z's here. So then pi has to be greater than inner perimeter divided by 2. So it's greater than 3. That's what we had. And it's, I mean, yeah, it's greater than 3, and it's going to be less than 3.46, which is using the z. You can see that, so the z there. And as you can see, yeah, so the error inside and error outside is pretty big there. But anyway, so if you keep doubling it all the way down to here, you get, so I have this one conditional formatting so that it basically the minimum here. So these are the minimum. Zoom in. So these are the minimum errors here. So as you can see for pi, 3.14, so we have a pretty good approximation right here. So we have it actually a pretty good approximation. If this is the exact one here, if we look at this one here, how accurate is this? It's roughly, so this is at 92645, 9265. So we're up to here. So we got it up to the, yeah, up to the 6. So that's, so it's going to be 1, 2, 3, 4, 5, 6, 7. So we got 7 decimal places accurate to pi. And so what we had, this is like 24,000 side here. But the problem here, it keeps getting worse and worse, the error here, because Excel isn't that accurate here. It only can go up to this, because you see these are all zeros here. Its accuracy is only up to, I think, 15, 16 digits here. So as you can see, yeah, you could count them up here. So then when you get really small here, like these are all not accurate here. Because Excel can't get that accurate. So basically with this method using Excel, we got up to, the most accurate we could get is this, like 13 iterations. Because once you go to 28, basically you just get 0, because these become 0 here. You can't, the number, the side length, it just becomes 0, or approaches 0, so you're just going to have 0 everything. and the error is just gonna be pi. So basically here, and so then for this one here, for Archimedes, he just stopped at 96 here because he was doing by hand, and that's just pretty ridiculously hard to split them up. And basically, yeah, he was just satisfied with that. It's hard to do because you have such small numbers here to be accurate. Then he got to 3.141, yeah, 0 there. So he was up to 3 decimal places close. And remember, it's in between this one, 3.142, which is true, because 1.5 is the greater one. Yeah, so then if you were to, let's say, put in so with this one you could just change it to, let's say, initial to 4. This is going to be the square, so the initial one here we have to change it to 2 divided by square root 2. So we get approximation, let's see, whatever this is read as the minimum here. So we get roughly 13 there. Again, roughly the same thing here, up to 6.5. So we got to 6.5 with both, whatever you start off with, polygon of 6 sides or a square here. Yeah, so that with that method here, we basically got to this. So pi is between these two right here, and in fact pi is equal to yeah, this value here. This is pi up to a bunch of digits here. So we got up to 965 here, and yeah, and basically Archimedes got, yeah, he got around 3.141, so he got 3 digits roughly, and he was yeah, this is pretty accurate for basically 2,000 years ago without calculators, or he didn't have basically advanced calculus or infinite series methods, which you can get these to like trillions of digits or and then whatnot. I'll show that later with infinite series in another video. Well, it's all for today. Hopefully you learned from it's basically how to derive pi, this number here. And another video I'll explain why is it even a constant with like a solid proof versus just a visual where you can see that the ratio changes. Yeah, when you make a bigger circle, the ratio is always going to be the same with circumference over diameter. I'll show why that is. But anyways, hopefully you learned about this. Also, you learned a bit about Archimedes. He's a pretty smart guy. That's all for today. Hopefully you learned, and remember you can download these notes and the Excel notes so you can play around with that Archimedes proof with that Excel table. That's all for today. Hopefully you learned. Stay tuned for another math easy solution.